Okay, so let's start the next session for today. So this is the session is entitled AI in Geological Survey Organizations, and our first speaker is Matthew Paice.
Thank you, Michael, for the introduction. And I will start by saying, despite what Michael said, that you can effectively cross out the AI bit from my bit of the talk, as it's mostly around machine learning. So I'm here today to talk about updating the UK superficial deposits thickness model using machine learning. So I'll give a brief introduction to superficial deposits and the existing superficial deposit thickness model, some of the previous workflow and the challenges that geologists and models have encountered with it, some of the data challenges and for a potential new model, the new model, some of the challenges we've got in terms of making it work, and finally how some of the discussions we've had have led to certain conversations around the future of VGS maps and how that may impact stakeholders and how they may react, and then I'll summarise the talk. So firstly, I'd imagine most of you are more familiar than I am, but the superficial deposit is effectively, as defined in our case, the depth to bedrock in the UK. And in this example, we can see a buried valley that has been filled in by sediment, and then the distance from that to there is what we refer to as the superficial thickness. Now, the previous method used a nearest neighbours interpolation to generate a model 1 to 5,000 scale across the entirety of the UK. There are a number of advantages of that. When the model was first developed in 2002, a technique was required that had very little computational overhead, and they also wanted a continuous surface to be produced. However, there are also other challenges in the fact that it won't capture nonlinear features that may be present in the data, and in particular, the way that this was implemented, it was implemented per quarter sheet. So for every quarter sheet of the Ordnance Survey map in the UK, there were joins. So it took geologists months and months to deal with both the joins and also to deal with any anomalies in the model, where you might get sudden wells or sudden shallowing in the depths, which then needed manual correction. For this small portion of the UK, there were 6 suspected anomalies and 5 of them required manual correction. So part of this work is to try and reduce the amount of, for one, joins that are present in the model, and 2, manual corrections that need to be made, so that we can get a new model or map out far more rapidly. So the SDTM was last updated in 2012, so that's 12 years without an update. And we've had a lot more observations in the meantime, so about 100,000 new borehole records are now available for us to use in this new model, either because of old classified boreholes becoming unclassified, as well as new data collection. So before I move on to talk about our main focus of the talk, which is the model, I just thought I'd go over some of the quality assurance issues we've had. One of the big ones is being rejected by geologists. So we have a lot of knowledge collected for over about 180 years of VGS, where they've gone, this geological interpretation is no good, or that borehole record is no good, and we have to try and capture that in the data that we're using. So we've gone back through previous modelling, previous SDTM data sources that we used for the model and picked out the geologist flags and said we are not using those boreholes. In addition, we're also using some numerical quantitative checks, and the majority are around looking at older borehole records and their accuracy in particular. So some of the older records tend to say that they'll give a coordinate, often to only 4 figures rather than any greater accuracy, and they'll say we're accurate to 100 kilometres, which when you're dealing with a point data source is not particularly useful, and we then get to the point where we look for more accurate points within the precision range of a borehole, and if they exist, we simply exclude that borehole. We've also got a number of duplicate locations, and so we tend to use deeper boreholes. And so I'll move on now to some of the challenges of the particular data set. So on the previous slide, we saw that we've actually rejected quite a lot of boreholes. If we look at the number of data points we have left, there are still a significant number. However, there are a lot of regions where data is quite sparse, and I was talking about using the nearest neighbours interpolation algorithm a few minutes ago. Nearest neighbours interpolation will not perform well in these regions, and it will require a lot of manual correction by geologists. Furthermore, the old surface, or SDTM, had no uncertainty surface. So a point here may be recorded at, say, 15-metre depth, and we've had inquiries from people drilling boreholes who then say, well, we've drilled down, and it was actually at 14-metre depth. And we're like, well, the nearest borehole is 100 kilometres away, so actually that's a really pleasing result for us, but the person who's written in the inquiry doesn't see it that way. So there's a really strong desire to have an uncertainty surface associated with it, although we do foresee there being some stakeholder problems in the fact that we're changing how we're delivering a data source. Furthermore, the data is really heavily right skewed. The majority of the depths are between 0 to 10 metres, but then it extends all the way out to about 187 metres in depth. And trying to find a likelihood function or a model which can fit that data set is quite challenging, as we'll see later. So our initial approach was to use a quantile gradient boosting tree, and as you can see, the result was relatively disappointing as we have heavy banding in the maps because there's no prior information in the model that near things should be related to each other, or that there shouldn't be discontinuities at this point. So it's effectively learning from the X and Y points in very heavily sampled regions, that should be the value at that point, and then drawing lines in the X and Y coordinate across the map accordingly. Now, this could be solved by transformations in the X and Y coordinates. We could include additional covariates. We're slightly constrained by the covariates we can use because there's a desire from the organisation to stick with 1 to 5,000 data sets that we are then producing. So we're producing the map 50-metre resolution. We don't want to use anything that's got less than a 50-metre resolution, just in case we begin putting points in the wrong quaternary domain, for example. So we've only got 3 covariates we're working with, so we can't really use a random forest or gradient boosting approach. So we began looking for an alternative, and through research we found a new method that's been developed by Sigrist et al. At the University of, or then at the Lucerne University, which I'll go over in a bit more detail on the next slide. But it combines a Gaussian process model for the nonlinear term, and then a Gaussian process model to provide a spatial correlation. And we were hoping that this would resolve some of the banding that you saw here, and it also provides an uncertainty surface. So a little bit more about the GP boost model. You can find an awful lot more information if you search Sigrist et al. 2022 and then GP boost. So what it does is it replaces the previous linear term in a Gaussian process model with an ensemble of trees, in our case a gradient boosting tree, providing nonlinearity, then a random effects term from a Gaussian process, an independent error term, and if you're using a non-Gaussian likelihood, a log link function, and for our case we used a negative binomial, which I'll come to later. That's a very recent result, so we're not completely trusting what we found. And then what you do is create a function and minimize it for both the gradient boosting tree and the theta term from the random effects or Gaussian process. And the process works by initializing a Gaussian process, then using a coordinate descent process to fit with the Gaussian process term, using a vector approximation to speed up, and then using a gradient boosting and or Newton boosting step to solve the equation. I've missed something quite important. So this Gaussian component gets put in as a tree within the gradient boosting model. It's taken into account spatial correlation, and then you fit the gradient boosting tree as you would normally. To get an uncertainty surface, you run a fourfold cross-validation process where you fit to 3 parts of the data and have a holdout quarter of test data, and then you can calculate the variance by using the fitted model to the other 3 components of the part and get some measure of uncertainty, but we're still in the process of understanding that at the moment. So our initial model, we fitted using a Gaussian prior as a starting point, and initially it looked quite good. So in the UK, we see that we have, in Norfolk particularly, varied valleys, where in dark blue you see a deeper superficial, as well as in other parts near Manchester, and just here. And generally it's shallower in mountainous regions, although perhaps not as shallow as we expected. We are seeing some of the measurement points coming through from the measure, so we see there the M5 cutting. And then if we look at the variance from purely the random effects, we can see it's behaving roughly as expected with very little variance on measured points, and we effectively end up with the road atlas of the UK, with it quickly becoming higher away from the UK. And we'll come back to that in a minute. However, there are a number of issues. Firstly, it's heavily under-predicting deeper superficials. Maximum depth in this particular model is around 70 metres, and it's tending to heavily over-predict at lower depths. So what we end up with is in mountainous regions, it believes there should be a superficial depth of around 7 metres, which is not correct. Whereas in Norfolk and other regions, you're tending to heavily under-predict the depths. So one of the ways we thought to deal with this was, instead of using the Gaussian likelihood, where we expect to encounter these kind of problems, was to use the negative binomial, which should handle the positive skew, the right skew. However, that isn't exactly how things worked out. If we were to look, Thomas, solely at the histogram, you might think that this model hasn't performed well at all. So we've seen a slight reduction in the over-predictions in mountainous regions, and you could argue a slight increase in depth, but it's still performing poorly in this region. However, if we actually look at the map, there's a marginal improvement. So we can see in this region, we are getting an increase in depth where we'd expect, and there's a slight decrease in the thickening across the entire of the UK, but it is very slight. But one of the, by producing this model, which only came out on Saturday evening, so it's a very new result, and I am slightly concerned at this point that I've done something wrong, because it looks very similar to the Gaussian, so I'll say that as a caveat immediately. But through communication with Sigris through GitHub, he recommended that we add an additional term, because the first time I ran the model, I missed out effectively the combined gradient boosting and random effects variance. So this is a combined version where we then see, as you would expect, on the right tail of the distribution, a very high variance, particularly in Norfolk, where you're seeing a lot of change, and then you can just about pick out a lower variance where the road networks remain. However, this is a very new result, and we haven't yet understood how or what is driving this variance. We're slightly concerned that there could be the model itself driving it, so whether you choose a Gaussian likelihood or a positive right skew distribution. We don't know how the random effects are contributing, and we don't know quite how the gradient boosting term is taken into account. And we're also not completely sure that this is a non-stationary error uncertainty. It could be some way between sort of stationary and non-stationary term. So we're going to look a lot more in detail in that. And I should also mention at this point, this is just one part of BGS's investigation into other methods for examining future mapping tools. So we're also looking at, as Charlie mentioned yesterday, we're looking at Charlie's approach. So the deep Bayesian approaches, we're looking at deep Krieging. As Fabian talked about, we're looking at a variety of Gaussian process models with speed-up routines, whether they're vector approximations or other sparse matrix approaches. Bayesian approaches, and then creating spatial correlation through a Gibbs term, and then from that exploring whether we get stationary or non-stationary uncertainty. So for different approaches and different mapping problems, we might choose a different approach. So they are currently under development, and we're hoping to have a paper out, I'd say some point soon, but we're in the process of validating all of these results. So I would also say that there's still some work to be done here, and there are some areas that perhaps actually some people in this room would be able to advise me on, because I've only been in the geostatistics part of machine learning for the last 2.5 years. We could potentially transform this signal to then improve the Gaussian process model fit, but in doing so, we would transform the variance, and the variance is calculated as part of the modelling approach. So we would then end up with a transformed variance that bears no relation necessarily, if back transformed, to something that we could use in an uncertainty process. So we want to look more in detail in that. So I've been trying to avoid transforming the data. I think I might have to try transforming the data and see what effects it has. Another thing I should point out is that this histogram is generated not from point data. So we haven't taken, say, a training set and then a validation set and then checked whether this histogram is matching the validation set. What we're doing is training the model and then producing a 1 kilometre in this case rather than 50 metre prototyping speed. Okay. And then pulling out at where borehole locations should be located, we're pulling out what depth the output 1 kilometre resolution grid gives us. So by using the 1 kilometre grid, we are biasing this result somewhat, because in places like Liverpool, where they've got 1,000 points per kilometre and some degree of change, we effectively say over that 1 kilometre we have one value. So if we're over thickening, we then end up with 1,000 values that are being reported as over thickened. But this is somewhat similar to how an actual geologist in the field would be using the model. We don't want to validate on point data because the person using the product is not using point data. They will drill a borehole, or they'll go to a location and say, what's the depth here? They will look at the map and go, in this raster square, it's saying it's this value. So we're getting some idea of what kind of problems might we encounter for a stakeholder using this particular approach. And that leads to some of the future mapping ideas and stakeholder discussions that come out of this work. So one idea is that instead of providing particular values, we will instead give greater than 10 metres, greater than 20 metres, 30 or 40. And this has been used in a buried valleys model that BGS have recently produced by Tim Kiersey. And this helps to reduce the problem of stakeholders phoning up and saying, we've dug a hole and it's 20 metres, it should have been 30 or vice versa. There's then an automatic range in the data without there being an uncertainty surface. We can also provide an uncertainty surface. We're also somewhat concerned in doing so that stakeholders may completely ignore it, depending on their level of familiarity with geostatistics or indeed what they're wanting to use it for. They may just look at the map and go, it's that value. Oh, there's something else. Never mind. Another approach is to, instead of being using fixed grid cells, so 50 metres in this case, we use an adaptive grid-based approach so that we could end up with blocks of colour which give a value over a certain region. So if, for example, in Scotland, where there are very few measurement points, we can then create a block that represents what the thickness may be. That has its own disadvantages in the fact that we then might just lose the accuracy at that particular point and the uncertainty surface becomes more challenging to calculate. And so I've quickly gone over an introduction to superficial deposits and the SDTM, previous workflows and the challenges and how we're still trying to address those. So by introducing this new approach over the entire of the UK per quarter sheet, we've already introduced the boundary problem, reduced the boundary problem, but we're introducing further challenges, choices for the new model, where we might be going from now, and how that impacts stakeholder discussions. And Michael, I believe you're just staying around for time.
Yeah, that's great. Thanks, Matthew, for that great talk. Any questions for Matthew?
Just, it seems to be a fairly straightforward one univariate interpolation with non-stationarity problem that you're trying to solve,
Yes.
right? So there are old methods that may work.
They may work. And
Universal kriging or intrinsic random function of order k actually models the trend with functionals that you define, and I think it would be nice to make a comparison with this method.
Yeah.
Because it seems like you're looking for a complicated, maybe complicated method for something that's there are ways to do it already.
There are potential problems with variograms of creep in terms of the data size. So it's about 400,000 data points, which makes inverting that matrix tricky unless you by approximations. Your other method, yes.
Okay.
I agree that we need to do more comparisons with other.
There are some accelerated versions for variogram calculation for big data.
Yeah. And I'm aware that there are other techniques that I need to, we need to look into at BGS generally. And this is a sort of the prototype starting point.
Thanks.
Thank you.
We have the time for another question.
Matthew, this is a really dumb question. Why do we need to know how thick the superficials are rather than which bits of them are gravel or sand or clay or silt?
So it's probably more of a question for the BGS products team, but traditionally it's been used by engineering geologists, I believe. But it's not my area of expertise, and I haven't got the answer yet from the geologist. But it's an existing BGS product that was developed in 2002 when there was a need for it.
Right.
And I know that there have been comments from people in this room who would like to know what the superficials are, rather than it just being a depth. They would like to know what it is at each depth, and also what it is in the region.
And can you confirm the thickness at the bottom
Yeah.
is defined by chronostratigraphy? It's the base of the quaternary,
Yes.
not when you go from crud to solid rock, which is
So-
what caused the Carsington Dam to fail.
So there's a number of definitions of it. So there's the engineering geology definition. There are even varying definitions within some of this borehole data we have to be careful with. We're going with the definition given by the borehole drillers of rock head, which should be the depth of a quaternary. But I don't believe it's the case in every single borehole.
A driller will call rockhead when he starts not getting his
Yes.
bonus because the borehole doesn't go down.
Yes, so that there is some, in terms of the drilling, slowing down and having to change drill bit. But it's not necessarily clear. And to get a clear answer, we'd have to go back through all of the drilling reports.
So the reason the Carsington Dam 40 years ago failed
Yeah.
because an idiot said rockhead is where we go into old geology, but that old geology was weathered to clay.
Yeah.
So when they built their dam, it slid on a layer of clay. Very embarrassing.
Yeah.
It wasn't rockhead.
Yeah.
There we go.
Thank you.
Okay, let's thank Matthew for his great talk.